Let's go on with the third exercise. We have to compute the following integral. So the contour is a polygonal curve. Vertices are given here, these 5 points. So Z1 is -1 minus I. So if here is 0, this is Z1. Z2 is 1 minus 2I. Z3 is 3. Z4 is 1 plus 2I. Z4. And Z5 is -1 plus I. So -1 plus I. Okay. It's a curve going around the origin once. And here, the main difficulty in the exercise is to understand the properties of the root function. So this function is not well defined and continuous everywhere. So we are going to take here a branch of this function. So let's consider the square root function. I denote it like this. So this is a function that goes from C minus the negative real axis and goes to the number with positive real part. And what happens when we act on with this function? So here maybe we can take the Z plane, and we have here the W plane, and the function square root brings the Z plane to the W plane. So this is the origin, and the function goes in the region when in this region here where the real part is positive. Maybe it's useful to write a formula for this function. So let's suppose that Z is equal to R times e to the I theta in polar coordinates, where R is positive. And now, since we are outside the negative real axis, theta would be a number between minus pi and pi. Then W equal to square root of Z is defined as square root of the norm R times e to the I theta over 2. And then here we see that if theta is in minus pi, then theta over 2 is in minus pi over 2, pi over 2. And therefore, W has exactly positive real part. And we will be interested in understanding what happens when we approach the negative axis. So let's say we have a point here minus S, where S is a positive number. And suppose we have some sequence Zn converging to minus S. With the property that the corresponding arguments, theta n, is positive. So we are approaching minus S from above. Then, according to the formula, what happens to Wn? Wn is the square root of Rn times e to the I theta n over 2. And we know that since Zn converges to minus s and theta n is positive, then Z Rn is converging to s, the norm of minus s, and theta n is converging to plus pi. Then we see that Wn is converging to square root of s times e to the I pi over 2, which is I, so square root of s times I. So if we want to depict this in the W plane, so we will have somewhere here square root of s times I, and then this will be the sequence Wn. And we can sum up this discussion by saying that the limit as z tends to minus s with the argument of z positive of square root of z is equal to square root of s times I. Then we can make a similar discussion if the sequence Zn converges to minus s, but with the negative argument. So same story. If Zn converges to minus s with the argument theta n less than 0. Now then what we find is that in this case we get a minus sign. So the limit as z goes to minus s for the argument of z, which is less than 0, of square root of z is equal to minus square root of s times I. Okay, this is due to the fact since theta n converges to minus pi, and then e to the I theta n over 2 converges to e to the minus I pi over 2, and this is minus. Okay, so now we have this. This is the relevant information that we need from the square root, and now we can use it to solve the integral. So here we have the problem that the curve gamma crosses the negative real axis. So what we are going to do, we are going to write this integral as a limit of integral over smaller curves. So we are going to break the curve here and there, and to consider approximated curves. So the approximated curves, we are going to start at z0, which is equal to minus 1 plus epsilon I, sorry, minus epsilon I, and start at z0 equal to minus 1, sorry, and end at z6 minus 1 plus epsilon I. So, and then the curve gamma epsilon polygonal curve going through Z0, Z1, Z2, Z3, Z4, Z5, and Z6. So what we find now is that the integral of gamma, the exponential of the square root of z divided by the square root of z of dz, this is the limit as epsilon goes to 0 of the integral over gamma epsilon, the same of the same function. And now the curve gamma epsilon has the property that is contained in a domain where the function x square root of z divided by square root of z is holomorphic. So function f from c minus the negative axis into c, defined by f of z equal to x square root of z divided by square root of z, is holomorphic. And so we know that if f is a primitive of this function, so it's a holomorphic function with f prime equal to f, then I can write the integral of gamma epsilon of f z dz. This is the integral of the derivative of big F. And we know that this is then equal to f of z6 minus f of z0, no? Because this is the endpoint of gamma epsilon, and this here is the end point, sorry, as the starting point of gamma epsilon. So now we have to find what this big F is. So if the small f is given with this formula, it's easy to see that big F can be taken as 2 times the exponential of square root of z. Now let's check this. So we have 2 times the derivative of the exponential of the square root. We use here chain rule, and we get exponential of square root of z times the derivative of square root of z. And this derivative is equal to 1 over 2 square root of z. So 2 goes away, and we get exactly f of z. So this is now the big F we have to find, and now we have to compute f of z6 minus f of z0. So this is 2 times the exponential square root of minus 1 plus epsilon I minus 2 times the exponential of minus 1 minus epsilon I. And now the thing that's left to do to compute this integral here is to see what happens when epsilon goes to 0. So let's call this equation star. So using star, we find the integral you have to compute is equal to the limit as epsilon goes to 0 of 2 exponential of square root of -1 plus epsilon I minus exponential of square root of -1 minus epsilon I. Now we can use that the exponential is a continuous function, so we get 2 times the exponential of the limit and same here. And now we know that these points, -1 plus epsilon I, are converging to -1. So -1 plus epsilon I are converging to -1 with the argument, this point set epsilon, with argument sorry, this was called Z, I think Z6. With argument of Z6 is positive. So this implies that the limit for epsilon going to 0 of square root of Z6 is equal to 1 times I. Also, we apply the formula up here. This formula here, let's call it star star. With S equal to 1. And the same thing we can now do for Z0. So Z0 is -1 minus epsilon I. So this converges to -1. But now with the argument of Z0, which is negative. So this implies that the limit epsilon going to 0 of Z0 is equal to -1 times I. And here we apply star 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 with S equal to 1, where star 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 is this relation here. Okay, so now we can plug in everything inside, and here we get 2 times the exponential of I minus the exponential of minus I. What is the moreover? To exponential I minus exponential minus I. We want to rewrite this. We can use the property of the sinus function. So this is 2 times 2I divided by e to the I minus e to the minus I divided by 2I. And so this is 4I times sinus 1. Okay, so then the end result is 4I times sinus of 1, but also writing in this way 2 times xi minus x minus I would be fine as well. Okay, so doing a recap, to prove this integral along the curve gamma, we observe that we can take this integral as a limit of the integral over gamma epsilon, where gamma epsilon is a curve which avoids the negative real axis, so that now the function we are integrating is holomorphic on the curve gamma epsilon. And once we know that the function is holomorphic on the curve gamma epsilon, we can use that if we know a primitive, this big F, then the integral can be written as the difference between F at the end point of gamma epsilon minus the integral of F, minus the value of F at the starting point of gamma epsilon. So this big F we found was easy to find. And now we have to pass to the limit. And to pass to the limit, we have here that we have to know what happens to the square root of Z6 and Z0. And for this, we saw right at the beginning with this discussion here that the limit is equal to square root of S times I if Z is converged to minus S and has a positive argument, or on the other side is equal to minus square root of S times I if Z is converged to minus S and the argument is negative. So in the end, the answer for this integral is 4I times sinus of